Proof of Theorem 10.1. Welcome, everyone. In our previous lesson, we introduced Theorem 10.1, which is a fundamental property in circle geometry. As a quick refresher, this theorem states that the tangent line at any point on a circle is always perpendicular to the radius that connects the center to that specific point of contact. Now, while we know this to be true, today we aren't just going to take it at face value. In this tutorial, we are going to walk through the formal geometric proof of this theorem, step by step, to understand the logical reasoning that makes this property a mathematical certainty. Understanding the setup. Now, before we dive into the actual logical steps of the proof, we need to be very precise about our setup. In geometry, we can't just start calculating. We must first clearly define our geometric components so we know exactly what we are working with. First, let's look at what is given to us in this scenario. Imagine a circle, and let's label its center as point O. We have a straight line, which we will call line X. Y. This line is a tangent to our circle, and it touches the circle at one specific point, which we'll call point P. Now, if we draw a line segment from the center, point O, to that exact point of contact, point P, we have our radius, which we'll refer to as op. So, our goal, or what we are to prove, is to demonstrate a specific relationship between this radius and our tangent line. Specifically, we want to prove that the radius op is perpendicular to the tangent line xy in mathematical notation. We would write this as op is perpendicular to xy. Keep this objective in mind, as the next slide will show you the logical steps we'll use to reach this conclusion. Step-by-step proof. To prove this theorem, we aren't just going to rely on what looks right in a diagram. Instead, we are going to use a very powerful mathematical concept, the idea of the shortest distance from a point to a line. Let's walk through this step by step. Step 1. First, we need to pick a point to test. We'll select an arbitrary point on our tangent line. Let's call this point Q$. Now, it's important that this point Q$ is any point on the line xy$ except for our original point of contact, P$. Step 2. Next, we need to determine exactly where this point Q$ is located in relation to our circle. Think back to the definition of a tangent we discussed earlier. A tangent line intersects the circle at exactly one point, which is P$. Because Q$ is on the line xy$ but is not the point P$, it cannot be on the circle itself. Therefore, point Q$ must lie outside the circle. Step 3. Now, let's compare the distances from the center of the circle to our points. Since we just established that point Q$ is outside the circle, the distance from the center O$ to this point Q$, which we call the line segment O'Q$, must be longer than the distance from the center to the edge of the circle. In mathematical terms, we can say OQ$ is greater than O'P$. Step 4. This is a crucial logical step. Remember, we chose Q$ as any arbitrary point on the line. This means our finding isn't just true for one specific point. The inequality O'Q$ is greater than O'P$ holds true for every single point on the tangent line xy$, with the one exception being the point of contact, P$. Because P$ is the only point that isn't further away, this implies that the segment op$ is actually the shortest possible distance from the center O$ to any point on the line xy$. Step 5. Finally, we apply a fundamental geometric property. In geometry, there is a rule that states the shortest distance from a point to a line is always the perpendicular distance. So, if op$ is the shortest distance, it logically follows that op$ must be perpendicular to the line xy$. This brings us directly to our conclusion. Now that we have clearly defined our setup, with our circle, our tangent line xy$, and our radius op$, let's dive into the actual proof. This is the core of our lesson. Conclusion. Now that we have established that the distance from the center to point P is the shortest possible distance to the line, we can reach our final conclusion. Since we have proven that the segment op is the shortest distance from the center O to the tangent line xy, we can apply a fundamental rule of geometry. The shortest path from a point to a line is always the perpendicular path. Therefore, we can formally state our result. OP is perpendicular to xy, which we write as OP is perpendicular to xy. This completes our proof. Real-world analogy, the bicycle wheel. Now, I know that formal geometric proofs can sometimes feel a bit abstract, so let's step away from the diagrams for a moment and use a real-world analogy to help this concept stick. To visualize what we just proved, I want you to imagine a bicycle wheel resting on a perfectly flat, straight road. First, think of the flat road as our tangent line, which we've labeled as xy. Next, look at the exact spot where the tire meets the pavement. That specific point of contact is our point P. Now, imagine one of the spokes of the wheel. This spoke starts at the center of the wheel, which we call O, and runs directly down to the point of contact. P. This spoke represents our radius, or the line segment OP. Finally, consider the angle. For the wheel to be balanced and to touch the ground at exactly one single point, that spoke must be perfectly vertical, meaning it is perpendicular to the horizontal road. If that spoke were tilted at any other angle, the tire wouldn't just touch the road at one point. The geometry of the contact would shift. This perfectly illustrates the logic we used in our proof. The radius is the shortest path to the line, and that shortest path is always perpendicular. Key takeaways. First, let's look at our definition-based logic. The entire foundation of this proof rests on the fundamental definition of a tangent. It is a line that touches the circle at exactly one single point. Because of this, every other point on that line must necessarily lie outside the circle. This leads us directly to our second point, the distance comparison. As we established in our step-by-step proof, if a point, let's call it Q, lies outside the circle, the distance from the center O to that point, Q, must be greater than the radius. In mathematical terms, we say OQ is greater than OP. Following this logic, we arrive at the concept of the shortest path. Since every point on the tangent line, except for our point of contact P, is further away from the center, the radius, OP, represents the absolute minimum distance from the center O to the tangent line xy. Finally, we apply the fundamental geometric rule. The shortest distance from a point to a line is always the perpendicular distance. This is the aha moment that completes our proof. Now that we have walked through the formal proof and seen how the bicycle wheel analogy helps us visualize the concept, let's pause and summarize the key takeaways from this lesson to ensure you have a solid grasp of the logic. Keep these 4 pillars in mind, because in our next slide, we will discuss some common pitfalls and mistakes that students often make when attempting similar geometric proofs. Common mistakes to avoid. First, be very careful about assuming perpendicularity. A very common error students make is stating that OP is perpendicular to XY simply because it looks that way in a diagram. In a formal mathematics exam, it looks right is not a valid reason. As we demonstrated in the step-by-step proof on the previous slides, you must justify your conclusion using the shortest distance logic or the method of contradiction that we just walked through. Second, make sure you aren't confusing secants with tangents. It is vital to remember that this theorem applies only to tangents. A secant line intersects the circle at 2 points, rather than just one. Because a secant has 2 points on the circle, there are 2 points at a distance equal to the radius from the center. This means the perpendicular distance from the center to a secant will actually be shorter than the radius. So, always verify that your line touches the circle at exactly 1 point before applying this theorem. Finally, pay close attention to your notation. Precision is key in geometry. When you write OP is perpendicular to XY, using the perpendicular symbol, you are making a specific mathematical claim, that the line segment OP meets the line XY at a 90-degree angle. Using the correct symbols ensures your mathematical communication is clear and professional. Now, before we wrap up today's session, I want to touch on some common pitfalls. As we've just seen in our proof, geometry requires rigorous logic, so let's look at some mistakes to avoid. With these points in mind, you should be well prepared to apply Theorem 10.1 to much more complex problems.